Welcome, curious minds, to the deep dive. Imagine you're trying to solve a massive, complicated puzzle, but the pieces are scattered everywhere, some hidden, some in different boxes, and some speaking entirely different languages.
Ah,
Frustrating,
yeah,
right?
totally.
Yeah,
Well, today we're handing you the ultimate toolkit to become a master puzzle solver in the digital world.
that's it exactly. Our mission with this deep dive is really to pull back the curtain on how data truly works behind the scenes.
Okay.
We'll explore how you ask it questions, how it's brought together from, countless sources, and how it flows through the very fabric of an organization's operations.
Right.
It's about giving you a true shortcut to being incredibly well informed quickly by demystifying the complex systems that underpin, well, nearly everything we do.
Absolutely.
hmm
Think about it. Every app on your phone, every online purchase, every interaction with a company, it
Hmm.
all generates and relies on data.
And that data needs to be extracted, connected, and understood within a larger context. So let's unpack this piece by piece, starting with the fundamental language of data itself, SQL.
Let's do it.
For our first deep dive today, we're getting hands-on with what's widely considered the universal language for databases, SQL, or structured query language.
Well, yeah.
Now, you might hear language and think, oh, this is going to be overly technical, but it's more like learning a set of powerful, precise commands. Once you grasp them, the way you interact with and understand information will fundamentally change.
It's really true. At its heart, SQL is how you communicate with relational databases. Now, for listeners who might already be familiar, a relational database isn't just some random pile of data.
Right, it's structured.
Exactly. It's a highly organized digital structure, kind of like a well-indexed library. Instead of stacks of books, you have tables, each designed to hold a specific type of information, say, customers, products, or sales orders.
Makes-
Within each table, data is organized into records, which are basically individual rows and attributes or columns, which define the specific characteristics of those records, like a customer's name, address, or maybe an order's date.
And SQL is your precise way of asking that incredibly organized library very specific questions to get exactly what you need.
Precisely.
While SQL can be used for creating new data, updating existing records, or even deleting information, which is incredibly powerful, by the way.
Super powerful, yeah. And needs care.
For most of us, especially in the realm of data analytics and informed decision-making, our focus is squarely on viewing and extracting data. It's about pulling out just the right pieces that match your specific analytical goals.
Think of crafting a SQL query as literally posing a highly structured question to the database. You might ask, show me all customers from California who purchased product X last month and spent over $500. The database, using its SQL interpreter, processes your request and hands you back a perfectly curated answer based on the precise criteria you provided. It's a very disciplined, very precise conversation you're having with your data.
And to have that precise conversation, you've got to know your way around the library, right? You need to understand the database's underlying structure.
Absolutely critical.
This means knowing which tables exist, how they relate to each other, and crucially, identifying their primary keys and foreign keys. These keys are the unique identifiers that act as the glue, sort of linking different pieces of information across your digital library. Without them, your data is just a jumbled mess.
Precisely. This is where data professionals rely heavily on tools like data dictionaries and data models. A data dictionary is essentially a comprehensive glossary for your database, defining every table, every attribute, their data types, and what they represent.
Like a legend for the map.
Exactly like a legend. And a data model, on the other hand, provides a visual map showing how all these tables are interconnected. They are your essential guides, revealing what data is available, where it lives, and how you can access it effectively. It's like having the full blueprint of your information architecture.
So how do we actually write one of these questions or queries? SQL queries are built from two fundamental types of elements: SQL commands and database elements.
Okay.
SQL commands are the language-specific keywords, the verbs of your data requests. We're talking about terms like select, from, join, group by, having, where, and order by.
The core vocabulary.
Yeah, the core vocabulary. And here's a little tip for readability. While SQL typically isn't case-sensitive for these commands, most analysts write them in uppercase to make them visually distinct from the actual data elements. Just helps it pop.
Definitely helps readability. And then you have the database elements. These are the nouns of your query, the actual names of your tables, the specific names of your attributes or columns, or the precise criteria you're filtering by.
Got it.
These must be spelled exactly as they appear in the database. Unlike the commands, the case of table or attribute names might sometimes matter, depending on the database system itself, but generally consistent, proper casing for readability is a strong best practice. It just makes your query easier to parse for anyone, including, your future self.
Future you will thank you. So when you combine these commands and elements, you form what SQL calls clauses. Think of them as the phrases that make up your data question. There's a required order for these clauses, and almost every functional SQL query you write will inevitably begin with two non-negotiable ones: select and from.
Absolutely. They are the absolute bedrock. You can't really do anything without those two.
Let's jump right into those foundational elements because they truly form the skeleton of virtually every query you'll ever construct. First up, the select clause. This is your "what do I want to see" declaration.
Its purpose is clear and straightforward. You use it to specify precisely which attributes or columns you wish to retrieve and view in your query results. Let's say you have a sprawling customers table, brimming with every imaginable detail: addresses, phone numbers, email, date of birth, purchase history, just a ton of stuff.
Right, the whole shebang.
Yeah, exactly. But for your current analysis, you're only interested in their first name, last name, and state.
Okay, just those three things.
In that scenario, your select clause would be as simple as select first name, last name, state. You're literally telling the database, just extract these three specific pieces of information.
And here's a really neat detail that gives you immediate control over your output. The order in which you list those attributes in your select statement directly dictates their order in your query's results.
That's super handy.
Yeah, so if you wanted a list organized like a phone book, you'd simply put last name first, then first name, like select last name, first name, state. That immediate visual customization is very powerful.
Very. Now, what if you're in a situation where you need every single attribute from a particular table? Instead of tediously listing out dozens of column names, which can be a real pain for wide tables.
Right. Oh yeah, I've been there.
SQL offers a convenient shortcut: select. The asterisk acts as a wildcard, meaning give me everything. So select will retrieve all attributes from a specified table in their original stored order.
Quick and easy.
It's a huge time saver, especially for quick explorations or when you truly need all available data. However, a quick professional tip: while select is convenient for ad hoc analysis in large production environments, it can be a performance killer by pulling unnecessary data.
Ah, good point.
And it's also a potential security risk if you're inadvertently exposing sensitive columns. A true data pro knows when not to use it for efficiency and security.
So use it wisely.
Use it wisely. Also, it's worth noting that the select clause can leverage various SQL functions, for example, string functions, to manipulate text values like combining names or extracting parts of a string, or mathematical functions for calculations. It's not just about picking columns.
Okay, so you've clearly articulated what you want to see using the select clause. The next logical step is to tell the database where to locate that data. And that, my friend, is the job of the from clause.
Yep. It's your "where is this data hiding" statement.
Exactly.
Exactly. The from clause precisely informs the database management system which table or tables contain the attributes you've specified in your select clause. So building on our previous example, if you wanted first name, last name, and state from your customer records, you would complete your query by adding from customers.
Simple enough.
This tells the database, go into the customers table and find those attributes.
And when you put these two fundamental clauses together, you've got your very first functional SQL query. Select first name, last name, state from customers. This isn't just a line of code. It's your foundational step to asking the database a direct, intelligent question.
Your first conversation with the data.
Yeah. You're selecting precisely what you need and telling the database exactly where to find it. It's elegantly simple, yet incredibly powerful, and it's the true starting point for refining your data extraction superpower.
Absolutely. The building blocks.
So we've mastered selecting specific columns and telling the database which table to pull from. But what if you don't want all the records in that table? What if you need to filter your results to zero in on something very specific, like customers from a certain state or sales above a certain amount?
Right, because usually you don't want everything.
Exactly. That's where the where clause becomes your best friend, acting as a powerful filter.
You're right. Think of where as the primary tool to apply a surgical filter to your query results, much like using a sophisticated filter in a spreadsheet program to weed out irrelevant data.
Like filtering in Excel, but more powerful.
Kind of, yeah. It allows you to dramatically narrow down your focus to only the data truly relevant to your specific analytical questions, cutting through the noise to deliver targeted insights. The basic syntax is quite intuitive. Where attribute name operator criteria.
And a crucial rule here, one that SQL will remind you of relentlessly if you get it wrong.
Yeah.
The attribute name must be spelled exactly as it appears in the database. No quotes around the attribute name itself.
Got to be precise.
Now, the interesting part is how you format the criteria, that specific value you're filtering by. That depends entirely on the data type of the attribute you're scrutinizing.
Precisely. Database attributes typically fall into categories like text, number, and date. For text data types, which are used for descriptive or categorical elements such as names, states, or product categories, your criteria must be enclosed in single quotes.
Single quotes for text. Got it.
So if you want to see only customers residing in Arkansas, you would write where state, ASRR. For a very common analytical need, you might also use the like operator for pattern matching, like where product name like laptop percent to find all products starting with laptop.
Ooh, like is useful for partial matches.
Very useful.
Got it. So if it's words or categories, quotes are essential. What about numbers?
For number data types, which represent quantifiable values that can be summed, averaged, or used in calculations, think sales price, quantity sold, or employee ID, there's no need for any formatting or quotes around the criteria.
No quotes for numbers. Easy.
If you want to see sales where the price was greater than $100, you'd simply write where sales price 100.
Okay.
And for date data types, used for transactional dates like order date or ship date, there are specific formatting requirements that vary slightly by database system, often involving functions to extract year, month, or day. But the core idea remains focused, filtering by a particular date or date range. Dates can be a bit fiddly sometimes.
Yeah, date formatting can be tricky depending on the system. Beyond the simple equal sign, SQL offers a suite of operators you'll use constantly with where and later with having. These include less than or equal to, greater than or equal to, and the often forgotten but powerful not equal to, or sometimes.
All the standard comparisons.
Right. And you can also combine multiple conditions using ND and or, for example, where state or DZA and sales price 500 to create highly specific filters.
So this is where you elevate your analysis from a broad overview to surgical precision. You move from seeing all the data to seeing only the specific data points that truly matter to your current analysis.
Cutting through the noise.
Exactly. It enables you to pull out those specific needles from the haystack, leading to much more targeted and actionable insights. This truly refines your data extraction superpower, giving you incredible control.
We've covered selecting specific rows and columns, but often the real power of data analysis isn't about looking at individual records. It's about seeing the bigger picture summaries, totals, averages.
The aggregate view.
Yeah. You want to know the grand total sales or the average quantity sold per product category. This is where SQL's aggregate functions come into play.
SQL aggregate functions are incredibly versatile. You use them directly within your select clause to calculate grand total or subtotal values from your data. The most common ones you'll encounter are SUM for total value, count for counting records, AVG for average value, MIN for the smallest value, and max for the largest.
SUM, count, AVG, MIN, max.
The classics.
The workhorses. When we talk about aggregating, we're literally talking about forming a group or cluster to get a summarized view. So aggregated data represents those totals or subtotals, allowing you to quickly move beyond the noise of individual records to a higher level, more meaningful perspective.
So instead of seeing every single sales order, you might want to know the total number of sales orders in your sales orders table. How would you do that with an aggregate function?
You'd use count. For instance, select count sales order from sales orders would return a single number, the grand total count of all orders.
Just one number representing the total. Yep. It's incredibly useful for getting a quick, high-level overview of the size of your entire data set. Or, if you wanted the total revenue, select some sales price from sales orders would give you the overall sales figure.
That makes perfect sense for grand totals. But here's the crucial question. What if I don't want one grand total? What if I want to see subtotals, like the total number of orders per customer or the average sales amount per product category?
That's where you group B by Y, right?
Ah, now you're asking the right question. That's precisely where the Group B by clause becomes indispensable. It's absolutely essential for generating those targeted subtotals based on specific categories or dimensions within your data. It allows you to segment your aggregates.
Okay, so it carves up the totals based on categories.
Exactly.
So if I wanted to see the total number of orders for each individual customer, how do I structure that?
You'd start by determining the descriptive field you want to group your aggregate by, in this case, customary.
Okay, group by customer.
Then you'd identify the field you want aggregate for counting orders. That would be sales order. Count the orders.
You'd place both the customer ID and the count, sales order ID, in your select clause. Then, crucially, you add the group by Y clause and include the same descriptive attribute you use for grouping, customer ID.
So whatever is in the select that isn't an aggregate needs to be in the group by Y?
Generally, yes.
Okay.
Your query would look like this. Select customer ID count sales ordered from sales orders grouped by customer ID.
And what's a common stumbling block here that SQL will relentlessly remind you about?
Great question. A very common error for beginners is to put a non-aggregated column in the select clause that isn't also in the group by Y clause.
I've hit that error many times.
We all have. For example, if you select customer ID, customer name, count sales ordered from sales orders grouped by customer ID, many SQL versions will throw an error because customer name isn't included in the group by Y.
Right, because how would it know which customer name to show for that customer ID group if there were somehow multiple?
Exactly. If you want to see the customer name alongside the customer ID, then customer name must also be added to the group by clause. Select customer ID, customer name, count sales ordered from sales orders grouped by customer ID, customer name. This ensures each row in your result truly represents a unique group based on all the non-aggregated columns.
That's a fantastic illustration and a super helpful tip for avoiding frustration. This is where data truly transforms from raw numbers into meaningful summaries. You're not just seeing the individual trees, you're able to see the different types of forests, how many trees are in each, and how they compare.
Nice analogy.
Enabling you to identify key trends, measure performance across segments, and spot outliers at a glance.
That's the goal. Actionable summaries.
So we've learned how to get grand totals and, more powerfully, how to get subtotals using Group BBY. But what if you only want to see groups that meet a certain condition after they've been summarized? For example, customers who have placed more than 10 orders or product categories whose total sales exceed a specific amount. You can't use where for that, can you?
That's a critical distinction you've nailed.
Yeah.
You are absolutely correct. While the where clause filters individual records before any aggregation happens.
Before grouping.
Before grouping, yes. The having clause is specifically designed to filter results after they've been aggregated using group by. You absolutely cannot filter aggregate measures directly with a where clause. You must use having.
So having is essentially where for your grouped data. How does its format compare? Is it similar?
It's very similar to where in its structure. The general format is having aggregate function attribute operator criteria.
Okay.
So the aggregate function part can be any of your aggregate functions like SEM, AVG, or count. The attribute is the field that's being aggregated, for instance, count, sales ordered, or sums quantity unsold.
And the operators are the same as what we discussed for where, like equals, greater than, less than.
Exactly. You use the same set of relational operators, date, A, E, E, and the Turkle A. The criteria part then represents the numerical value you're filtering by for that aggregated result.
Makes sense.
For example, if you wanted to see only those customer groups where their total quantity sold exceeded 200 units, you'd append having some quantity sold 200 to your query after the group BBY.
That's a really crucial distinction and a common point of confusion for new data analysts, where before grouping, having after grouping.
You got it.
It provides an even finer level of control, allowing you to highlight only the most significant or relevant aggregated groups. You're not just summarizing everything, you're zeroing in on the summaries that actually tell you something impactful for your analysis.
Focusing on the exceptions, or top performers, for example.
Exactly. This is another key step in transforming raw data into truly actionable intelligence, helping you focus on the exceptions or the top performers.
Essential for analysis.
So far, we've focused on pulling data from a single table, effectively asking very precise questions about one specific data set. But here's where the true power of SQL really shines, and it's an absolute game changer for data analysts. Connecting different data sources using joins.
Yes, the joins. This is where it gets really interesting.
This is where you bring disparate pieces of information together to form a holistic picture.
You've hit on the core of relational databases. They're specifically designed to reduce redundancy by storing related details across multiple interconnected tables.
Right, don't repeat yourself.
Exactly, the DRY principle. For instance, imagine you're analyzing sales data, and you're interested in knowing not just what was sold, but the customer's phone number associated with each sale. Customer details, including phone numbers, are typically stored in a customer's table,
Okay.
while individual orders are in a sales orders table. You wouldn't want to duplicate every customer's full address and phone number for every single order they place. That would be incredibly inefficient and, frankly, error-prone.
Yeah, imagine updating an address in hundreds of order records. Nightmare.
Total nightmare. So how do we bring these separate pieces of the puzzle together without manually copying and pasting, which sounds like a nightmare for large data sets?
So there must be a better way.
There is. The prerequisite is understanding your database schema, that visual blueprint that depicts how your tables are structured and, most importantly, how they relate. You'd identify the common primary keys and foreign keys that link them.
Those keys we mentioned earlier.
Exactly. In our example, both the customers table and the sales orders table would undoubtedly share a common link, typically customer E. The customer E in customers is its primary key, uniquely identifying each customer.
One unique ID per customer.
Right. And in sales orders, it would be a foreign key, pointing back to a specific customer in the customer's table. This customer D is your bridge.
Okay, so once we've identified that common link, that bridge, how do we perform the join? And are there different types?
Yes, there are several join types, but the two you'll use most frequently are inner join and left join.
Inner and left, okay.
Let's start with inner join. An inner join is like looking for common ground. It retrieves only the data where there's a perfect match in the matching key in both tables.
Only where they match perfectly.
Perfectly. If a record exists in one table but has no corresponding match in the other, it will be completely excluded from your results.
So it's looking for that perfect overlap, only showing records that are present in both data sets based on the key.
Exactly. The template for an inner join is from table 1 inner join, table 2 on, table 1.matching key, table 2.matching key.
On is the key part there, specifying the link.
Precisely. The on-end clause tells SQL how the tables are connected. A key detail for inner joins is that the order of table 1 and table 2 does not matter. You can put customers in the from clause and sales orders in the inner join clause, or vice versa, and your final result set would be identical.
Doesn't matter which comes first for in. Okay, can you give us a concrete example?
Sure. To select all the matching data from both the customers and sales orders tables, you'd write, select from customers inner join sales orders on customers, customer ed, sales orders, dot customer ed.
Selecting everything from both where the customer aids match.
Exactly. Now here's a crucial implication. This query would not return any sales orders that somehow didn't have a linked customer ID, nor would it return any customers who haven't placed an order yet.
Ah, okay, so only customers with orders and orders with customers.
Correct. It only shows you the records that exist and perfectly match in both data sets where the customer ID corresponds.
That makes a lot of sense for getting only actively related data, but this brings up a common analytical problem. What if I want to see all my customers, even the ones who haven't placed an order yet? An inner join wouldn't show them, and that could really skew my understanding of my total customer base versus my active buyers.
That's precisely where the left join comes in, and understanding its nuance is a key insight for any data analyst.
Okay, the left join. How's it different?
Unlike inner joins, a left join will provide data even if there isn't a match in the second table. It retrieves all data from the left table. That's the table you specify in the from clause.
The first table mentioned.
Usually, yes, the one in the from. And it pulls any matching data from the right table, the one mentioned in the left join clause. If there's no match in the right table for a record in the left table's data is still returned, but the attributes from the right table will show NLL values.
NLL meaning empty or no value found.
Exactly. So the left table is the one whose data you want to see completely, regardless of a match. It's like your source of truth for that particular query.
Ah, okay. I want all of this table and any matching data from that other one.
Precisely. The template is from table 1 left join, table 2 on table 1.matching key equals table 2.matching key. And this is where the order does fundamentally matter.
Order matters for left join.
Absolutely. Table 1 in the from clause is your left table, whose data you want to see entirely. So to see all customers, even those without any sales orders, you would ensure customers is in the from clause and sales orders is in the left join clause.
From customers left join sales order.
Right. This way, every customer record will appear, and if they haven't placed an order, their sales order columns will simply be NNLL.
This is a huge distinction for anyone analyzing data. Many new analysts default to inner join, thinking they just want matching data. But a critical insight is recognizing when a left join is essential to avoid completely missing a significant part of your dataset.
Like those customers who haven't bought anything yet.
Exactly. Which could distort your market size analysis or show a falsely high conversion rate. Join-ins are like connecting the pieces of a complex puzzle, allowing you to build a complete picture from fragmented data. Understanding the difference between inner and left is absolutely crucial for getting the right perspective and answering your specific analytical questions correctly.
It really unlocks the depth of data analysis and helps you tell the full story. And that covers the primary SQL commands that will empower you to interact with relational databases and pull precisely the data you need.
Okay, let's quickly recap the SQL commands we've just covered because they truly are the foundational building blocks for querying data effectively.
Sounds good. So select is your what. It's required as the first clause and indicates which attributes or columns you want to view. Think select product description, sales price, or select for everything with that mental note about performance.
Right.
Or even select customer issued, some quantity sold when you're aggregating.
From is your where. It's usually the second clause and tells the database which table or tables the requested attributes are located in, like from products.
Where is your primary filter for individual records? It surgically narrows down results based on specific criteria, such as where sales price 100 or where state equals AR. Remember those quotes for text.
Group by Y is for creating subtotals. When you need to aggregate data into meaningful categories, this clause is necessary, like group by customer ID, to get aggregated results for each customer. And don't forget to include all non-aggregated select columns here.
Crucial rule. Having is the filter for your aggregated data. It's similar to where, but specifically works on the results of aggregate functions. For example, having some quantity sold 200 to show only groups that meet a certain threshold after summarization.
And finally, join and on are for connecting different tables. Join specifies the second table you want to link, and on indicates how the tables are related through their primary and foreign keys, like from customers inner join sales orders on customers. Customer E equals sales orders dot customer ID. Mastering the distinction between inner and left joins is pivotal for telling the right data story.
These commands, when combined strategically, allow you to extract incredibly precise and meaningful information from vast datasets, transforming raw data into actionable insights for any kind of analysis. It's not just about querying, it's about asking intelligent questions.
That's a fantastic summary. So we've just spent a good chunk of time diving deep into SQL, which is perfect for interacting with the structured world of relational databases. But here's the thing. In the real world, the data you need for accurate reporting and impactful decision-making isn't always neatly contained in one single relational database, or even just within one set of tables.
Yeah, life's rarely that simple, is it? While SQL gives you immense power within a specific database, real-world reporting and analytics often demand pulling data from entirely different data sources altogether.
Different systems, different formats.
Exactly. Imagine a company trying to understand why a new product launch failed. You might have sales data in one database, website browsing behavior in another, customer service interactions in a third, and marketing campaign performance maybe just sitting in a spreadsheet somewhere.
Oh, okay, that's scattered.
Very scattered. This is where data integration becomes absolutely critical.
This is all about breaking down what are often called data silos. Each department or system might have its own isolated pool of data, and without integration, you're only ever getting a fragmented, incomplete view.
Seeing only one piece of the elephant.
Right. Data integration is about connecting these disparate pieces, making them talk to each other to gain a truly holistic 360-degree view of your operations, your customers, or your market. It's literally bringing all the puzzle pieces to one table.
The good news is that you don't always need to build complex custom solutions from scratch. Many popular data analysis and visualization tools come equipped with powerful built-in integrations.
Oh, like the tools people already use.
Yeah, think about applications like Microsoft Excel, Power BI, Tableau Desktop, or Alteryx. They all have connectors that can link up with an abundance of common applications, major data warehouses, and various database systems. They're designed for this.
So you're not always starting from zero. And here's where combining these built-in integrations with the SQL queries we just discussed can make the process incredibly efficient.
Absolutely. You can use SQL to intelligently extract and limit massive datasets from their source systems to only the necessary information.
Pre-filter the data using SQL.
Exactly, pre-filter it, which makes the subsequent integration process smoother, faster, and way less resource intensive. Why pull terabytes if you only need a few gigabytes, right?
Makes total sense. Less data to move around.
Let's consider some real-world applications. where data integration is not just useful, but a strategic imperative, a total game changer for businesses. Take financial analysis, for example.
Okay.
It's common for analysts to combine an internal company's financial statements, perhaps from their enterprise resource planning or ERP system, with external market data.
Like what kind of external market data? Give us an example that really illustrates the power of combining these.
Sure, data from online financial databases such as Bloomberg or Yahoo Finance, or even publicly available economic indicators like interest rates, inflation, GDP figures.
Okay. Macro level stuff.
Right. By integrating these two distinct sets of data, an analyst can not only compare a company's financial performance against its own historical trends, but also benchmark it relative to its industry peers.
So are we doing well compared to ourselves and compared to the competition?
Precisely. For instance, integrating internal sales figures with external consumer confidence indexes and interest rates can reveal whether a dip in sales is purely an internal issue, or maybe it's part of a broader economic trend affecting everyone.
Context is everything.
It really is. I heard about one retail chain, for example. They integrated website browsing data with in-store purchase history.
Online and offline. Okay.
Yeah. They uncovered that customers who spent significant time viewing product A online, but ultimately bought product B in store, were like 30% more likely to return items within 60 days.
Whoa, that's specific and probably costly.
Very costly. This insight, impossible with fragmented data, allowed them to proactively send targeted pre-purchase information about product B to those specific customers, which led to a significant drop in returns and actually increased customer satisfaction.
That's brilliant. An insight that wouldn't even exist without connecting those dots. What about in operational analysis, like manufacturing or supply chains?
Great question. For operational analysis, relevant data is often scattered across different production databases, planning systems, or various spreadsheets. Integrating this data is key to making informed operational decisions and assessing performance.
Makes sense. Need the whole picture.
For instance, combining data from a production database which tracks what's being manufactured with supply chain data, perhaps from inventory management systems or logistics platforms, is incredibly powerful.
How so? What specific operational insights does that give you?
Well, this combination helps analysts identify operational inefficiencies like over- or underproduction, which can silently drain profits.
Making too much or too little?
Exactly. If your production data shows you're making more units than your supply chain can efficiently move, or your sales team can sell, you might have costly overproduction leading to excess inventory and storage costs. Big problem.
Wasted resource.
Right. Conversely, if demand is consistently high, but your production output is low, given your supply chain capacity, you might be underproducing and missing out on significant sales opportunities, just leaving money on the table.
Ouch.
This integrated view allows for optimized production schedules, better inventory management, and much more effective resource allocation across the entire operation. It helps companies avoid costly guesswork and pivot based on real-time connected insights.
It's clear then that data integration isn't just a technical concept or some buzzword. It's a strategic imperative that empowers businesses to make smarter, more data-driven decisions across all functions, from finance and marketing to operations and customer service.
Absolutely. It's about getting the full story, not just fragmented chapters. And that's where true competitive advantage often lies.
We've talked about extracting data with SQL and bringing it together through integration. Now let's shift gears to how we visualize the flow of these processes and the data that supports them.
Process mapping. Very important.
Because understanding how a business actually operates and where its information moves is just as vital as understanding the data itself. Without that context, you're looking at numbers in a vacuum.
Absolutely. Think about any large organization. It's an incredibly complex web of numerous processes, from onboarding a new employee to fulfilling a customer order. And each of these processes is supported by vast amounts of data.
It can get messy fast.
Oh, yeah. Trying to understand all that purely from written descriptions or raw data tables can be overwhelming, quickly leading to confusion and missed opportunities. Visualizing these steps and data flows helps explain how a business actually works,
How?
allowing you to understand when data is created, who is responsible for it, and critically, how it's used at each stage.
So we're talking about drawing detailed pictures of how things happen. What are the standard tools for that?
Yes, exactly. Flowcharts are common tools for depicting process or data flows. They help analysts visually map out current processes, analyze them for potential bottlenecks, redundancies, or control gaps, and then envision improvements.
Finding the sticking points or weak spots.
Precisely. This could be about making them more effective, more efficient, or strengthening internal controls for compliance. There are various templates, but today we'll focus on two widely recognized and powerful types: Business Process Modeling Notation, or BPMN for activity models,
BPMN.
and Data Flow Diagrams, or DFDs, for tracing data flow.
Okay, BPMN and DFDs. BPMN sounds like a bit of a mouthful, but it's crucial for standardization, right?
It is. BPMN is a highly standardized modeling tool. That standardized word is key.
Yeah.
It means it has a globally recognized set of symbols and rules specifically designed to depict business processes.
So everyone uses the same shapes and lines, basically.
Pretty much. This standardization is incredibly valuable because it promotes a common language. Imagine engineers in different countries or different departments needing to communicate about a complex process. BPMN ensures everyone is literally on the same page, vital for clear communication, robust documentation, continuous improvement, and effective management of business processes across an organization.
So it helps different teams or even different companies understand each other's work better, eliminating ambiguity. That makes sense. And you mentioned the significant benefit related to automation.
Precisely. A really significant benefit of detailed BPMN models is their potential to help identify process areas that are prime candidates for automation.
Finding things robots can do.
Essentially, yeah. The rule of thumb here is simple. The more rule-bound a process is, meaning it consistently follows a predictable set of decisions and actions, the easier and more cost-effective it is to automate.
If it's always the same steps, automate it.
Right. Once you've modeled a process with BPMN, you can clearly see how many steps and decisions are rigidly rule-based, or if they require subjective human judgment. Automating repetitive, rule-bound tasks can lead to significant cost savings, dramatic increases in efficiency, and reduced human error, freeing up people for more complex, value-added work.
That's a huge win for any organization looking to streamline operations. So what are the core elements we need to understand in a BPMN diagram to start reading these maps? What are the shapes?
Let's break down the most common symbols and rules you'll encounter. First, we have flow activities, which are typically organized using the metaphor of pools and swim lanes.
Pools and swim lanes, like a swimming pool.
Kind of. Pools are used to quickly showcase how many organizations or major participants are involved in a given process. Every BPMN model needs at least one pool, which represents the internal organization involved.
Okay, the main company is a pool.
Yeah. For instance, in a sales process, you might have a selling internal organization pool and a separate customer pool. But if the process is entirely internal, like payroll processing, you might just have one pool representing your company.
And then swim lanes carve up the pools, like lanes for swimmers.
Exactly. Swim lanes are more granular. They indicate the segregation of duties or different roles within a single organization, within one pool.
Ah, so who does what inside the company pool?
Right. So, continuing our selling organization example, you might divide that pool into lanes for a sales representative, a cashier, and a warehouse team to show clearly who does what within the overall process. It's fantastic for identifying handoffs and responsibilities.
Got it. Organizations are pools, roles are swim lanes. What's next in the diagram elements?
Next, we have events, which are depicted as circles. Events describe how a process begins or ends, or a significant occurrence during its execution. They aren't actions themselves, but rather triggers or indicators of completion.
Circles for start, stop, or changes.
Correct. The thickness of the circle's border tells you what type of event it is.
So a start event is a smooth, thin-lined circle.
Yes, and every pool must begin with one and only one start event. It's based on pools, not individual swim lanes, meaning there's just one definitive starting point for that entire organization's involvement in the process you're modeling.
One clear start per pool. And end events are bold circles.
Correct. Every pool must end with at least one end event. You can, and often do, have multiple end events if there are different ways a process might conclude.
Like success or failure.
Exactly. Perhaps a successful completion, a cancellation due to an error, or a specific outcome like an approval versus a rejection.
And intermediate events are the ones with two lines. What do?
Those are two-line circles, and they aren't always required in every diagram. But they come into play when something significant happens during the process that changes its course, or is a waiting state. Think of it as an interrupt or a trigger that occurs between the start and end.
Okay, like a pause or a message arriving.
Exactly. This could be a time delay, a message received from another system or participant, or an error condition that needs to be addressed before the process can continue.
Okay, so we have who's involved, Pools and lanes, and when things begin, change, and stop events. What about the actual work, the actions in the process?
Those are tasks represented by rectangles with rounded edges.
Rounded rectangles for tasks.
Yep. Every single action in a process, whether it's performed by a person, an automated system, or even a piece of software, is documented as a task. It's crucial to break down each distinct step into its own task.
Be specific.
Very specific. So for a sales order process, instead of one vague handle order task, you'd have explicit steps like input customer name, then select product, then select quantity, and verify payment. Each one is a separate, discrete action.
So once you have your pools, lanes, events, and tasks, how do you connect them all to show the flow of activities, the arrows?
That's where connecting objects come in. First, we have sequence flows, which are smooth-lined arrows.
Solid lines.
Solid lines, yes. These connect every object within one pool to depict the precise order and flow of the process. BPMN models are traditionally read from left to right, top to bottom. The start event kicks off the process, with a sequence flow extending to the first tasks, and then each object receives and sends sequence flows until the process culminates in an end event. They are literally the pathway the work takes.
So sequence flows are strictly internal to a pool. What if you need to show communication between different pools, like between your selling organization and the customer pool we talked about? How do they send information back and forth?
That's when you use message flows. These are visually distinct, shown as dashed arrows.
Dashed lines for messages between pools.
Correct. Message flows only function to indicate communication between two separate pools. They should never be used within the same pool to indicate communication between lanes. That's what sequence flows are for.
Big distinction. Sequence flows inside, message flows between.
You got it. The direction of the dashed arrow indicates who is sending the information and who is receiving it. For instance, the selling organization might send an invoice message flow to the customer pool, or the customer might send an order request to the selling organization pool.
That distinction between internal sequence flows and external message flows is absolutely key to understanding BPMN. And finally, what about those critical points where the process path might diverge based on a decision? The forks in the road.
That's handled by gateways, which are shaped like diamonds.
Diamonds for decisions.
Right. Gateways represent decision points where the process path can diverge into multiple outcomes. You use a gateway when a task doesn't have a single direct next step, but rather multiple potential outcomes or directions based on a condition.
So it's not an action itself, but a question or a condition, like, is payment approved?
Precisely. A gateway is always phrased as a question or condition, not an active task. So there shouldn't be any active verbs in its annotation. It might read, sufficient quantity available, rather than check quantity.
Okay.
A crucial rule for effective BPMN modeling is that task objects should always have one and only one sequence flow exiting them. If there are two or more potential exits or flows away from a task, then a gateway is always needed immediately after that task to manage that divergence logically.
So if after a process order task, the next step could either be ship order if payment is confirmed, or follow-up payment if it's pending, you'd need a diamond gateway there.
Exactly. The gateway would represent the payment confirmed question, and then two sequence flows would exit the gateway, each labeled with the condition, yes, no, and leading to a different path based on the answer. This ensures clarity on all possible outcomes.
Wow. Okay. BPMN is like drawing a detailed, standardized map of how work gets done, revealing potential bottlenecks, redundancies, communication gaps, and prime opportunities for automation and efficiency. It's an invaluable tool for process improvement and system design.
It really provides that structured view. That's a profound way to look at it. BPMN gives you the bird's eye view of who does what and when. It's a flowchart on steroids, really.
So BPMN models provide an incredible standardized map of what happens in a process, who's involved, and how the activities flow.
Wow.
But what about the data itself? How does it actually move through that process from one step to the next or in and out of storage?
Like the data's journey.
Yeah, that's where data flow diagrams, or DFDs, come into play. They give you an even more granular look at the information's journey.
That's right. DFDs are another standardized tool, offering a more granular level of detail about how data moves through a process or system that BPMN activity models alone might provide. While BPMN can indicate where data is stored or accessed, DFDs zoom in specifically on the data's journey itself, its inputs, outputs, and transformations.
Focusing purely on the data trail.
Exactly. And interestingly, DFDs use even fewer object types than BPMN, which makes them quite concise once you learn the symbols.
Fewer objects sounds good for clarity. What are these core DFD objects we need to know?
First, we have the process. This is depicted as a rounded rectangle or sometimes a circle. A process in a DFD represents any action that transforms data and produces a new output.
So similar to a BPMN task, but focused on data change.
Precisely. Unlike BPMN tasks, DFD processes are all about the data transformation. The labels for processes are typically short action sentences like input customer information, process payment, or generate report.
So it's the point where data is actively changed or used to create something new. What about the data itself? How is its movement shown?
That's the data flow, represented by an arrow. It indicates the direction data travels between processes, or to from data stores, or to from external entities.
Arrows for data movement.
Right. Importantly, data flows are always labeled to clearly show what data is flowing, for example, customer contact details, payment details, or order confirmation. These arrows can be curved or straight, as long as the direction and label are clear.
Always label the arrows.
Got it.
And where does all this data live when it's not actively flowing, when it's just sitting there waiting to be used or stored for later?
That's handled by the data store or warehouse, which is typically an open-ended rectangle.
Open rectangle for storage.
Yep. This object represents any location where data is stored for later use. This could be anything from a sophisticated electronic database to a simple SharePoint folder, a spreadsheet, or even an old-fashioned physical filing cabinet. It's essentially where data comes to rest, temporarily or permanently.
Okay, databases, files, folders. And finally, what about anything that interacts with the system but isn't actually part of the system we're diagramming, like the customer or the bank?
That would be the external entity or terminator, represented by a square.
Squares for outside things.
Exactly. This object indicates an external organization, a group of people, or a different department that either sends data to or receives data from the system being diagrammed. They are outside the scope of the specific process you are modeling, but are crucial points of interaction. An example could be a customer sending an order, a bank receiving a payment deposit, or a regulatory agency receiving compliance reports.
That makes perfect sense. Can you walk us through a simple yet illustrative example of how these objects connect in a DFD to show a data journey? Let's tie it together.
Certainly. Let's trace a simplified scenario for processing customer orders and payments. You might start with a customer, an external entity, so square, who sends data, a data flow arrow labeled customer order request, to a process, customer orders. A process, so a rounded rectangle.
Okay. Customer square sends order request arrow to process order rounded rectangle.
Exactly. This process customer orders might then interact with a customer relationship management system, which is a data store, an open rectangle, to retrieve or update customer details. Another labeled arrow showing data flow both ways, perhaps, or two separate arrows. It might also interact with a product inventory database, another data store, to check product availability, another labeled arrow.
Okay, so the process customer orders is both receiving data and interacting with multiple data storage systems, pulling and pushing data via labeled arrows. What happens after that, especially with payment?
Once the order details are validated, the process customer orders might then send payment details, another data flow arrow, to a subsequent process, perhaps a process payment, another process rounded rectangle.
Okay, payment details arrow goes to process payment.
Right. This process payment might then update a cash receipt database, a data store open rectangle. And finally, once the payment is cleared, a payment deposit, a data flow arrow, goes to the bank, which is another external entity square.
That example really clarifies how granular DFDs can be. If BPMN shows us what happens, who does it, and when, then DFDs show us where the information goes and how it transforms during those happenings.
Precisely the difference. BPMN for process flow, DFD for data flow.
They are absolutely essential for anyone wanting to truly understand the data life cycle within an organization, tracing every piece of information from its origin through its transformations to its final destination.
They are critical for diagnosing where data might be held up, transformed incorrectly, or simply lost in a complex system, and often reveal surprising inefficiencies that a simple process map might miss. They're indispensable for ensuring data integrity and for designing new systems where data flow is paramount.
So we've taken quite the journey today on the deep dive. We started by understanding how SQL empowers you to precisely extract specific data from relational databases.
Asking the right questions.
Like a master librarian pinpointing exactly the information you need, avoiding common pitfalls like using select in production or mistaking where for having.
Then, we expanded our view to data integration, seeing how connecting disparate data sources, whether different tables within a database or entirely different systems like an ERP and external market data, unites fragmented information for a truly comprehensive, holistic view,
Breaking down those silos.
breaking down those pesky information silos and revealing previously hidden insights.
And finally, we explored how BPMN and data flow diagrams provide invaluable maps of processes and data flow, helping us visualize not just what happens in an organization, but how the work gets done, who does it, and critically, where data moves through it.
Seeing the whole system.
This allows for identifying inefficiencies, opportunities for automation, and ensuring the right information gets to the right place at the right time.
Our mission with this deep dive was to give you a shortcut to being well-informed, not just about what these tools and concepts are, but why they matter, how they're applied in the real world, and how they all contribute to understanding and optimizing the incredibly complex systems that power our modern world.
So the next time you fill out an online form, make a purchase, or interact with a company's customer service, can you begin to visualize the SQL queries running behind the scenes to pull up your information?
Can you picture that selectee statement firing off?
Yeah. Can you imagine the BPMN activity model that dictates each step that customer service representative or automated system is taking, and then maybe zoom in with a DFD to see exactly where your data is flowing?
How might understanding these underlying structures change your perspective on everyday digital interactions or even the processes in your own life, at work or, at home? Perhaps identifying a bottleneck in your morning routine or a missed data point in your personal budget.
We encourage you to look for these patterns and connections in your own world, because once you start seeing the hidden architecture of data and process flow, the world of information truly opens up, giving you a powerful lens through which to understand, analyze, and even improve almost anything.